Good morning, good afternoon, good evening. Welcome to this 13th webinar in the CPT Webinar Series by Eijkelkamp North America, where we're going to talk about precautions when performing CPT. For those of you that attended the webinar last month, you know that we talked about performing CPT in accordance with the standards. And you can find that webinar on our YouTube channel, as Troy already mentioned. In that webinar, I talked about the various standards, being the ASTM standard, be it the ISO standard, on how to perform CPT. And the vast majority of that presentation was linked to the ASTM standard. Not that the ASTM standard is better than the ISO standard, but since it is Eijkelkamp North America who's producing these webinars, we use the American standard. But by and large, the content of both standards is about the same. And what you see on the screen right now is the table of content of that standard D5778, which was last updated in 2020. We went over this standard pretty much, but at the same time, I covered quite a bit of text in that standard. And in this webinar, again, if you see any blue boxes, that is text directly coming out of this ASTM standard. But what I mentioned also in that webinar was that you cannot rely on the webinar to perform CPT perfectly or adequately. In order to do it successfully, you need to read the standard. And I also mentioned in there that the webinar was falling short to some extent because we did not cover hazards and interferences. And sure enough, just as Troy mentioned, if you have a suggestion about a topic, let us know. Quite a few of you came back to me and said, well, can you do a presentation on these hazards and interferences? Can you tell us a little bit of things that can go wrong while you perform CPT? And that's the reason why we set up this webinar this month in May, Precautions when performing CPT, with the title so that this doesn't happen. Basically, what you see there is a rod that is obviously broken. That's the last thing that you want to see happening when you perform CPT. And we're going to talk about some of the things that you need to be careful look out for, so that things don't go wrong when you're out in the field. But when we talk about precautions when performing CPT, the first thing that I do have to talk about is travel to and from the job site. Let me give you some statistics to explain why I'm saying that. In 2018, there were more than 5,200 fatal occupational injuries in the United States, which basically means fatalities that were job-related. Out of those 5,250, roughly 1/5, a little less than 1,100, were in the construction industry, which is our industry. Geotechnical engineering group obviously serves the construction industry, so that's our industry. And out of those 1,080, 250 were transportation related. Which means that roughly a quarter of all the deaths in our industry are caused by going to or coming from the job site. And that's why the first thing I want to highlight is travel to and from the job site. We need to do that safely. We need to make sure, because let's face it, CPT is not being done in your office. You need to go out to the job site, you need to travel to the job site, and you need to come safely back to the office. And that's why we need to pay proper attention to this, because this is obviously an area where things can go wrong. Also, are there incidents? What you see here on the left-hand side was a CPT operator who traveled, I don't know how many miles over a paved road, and came to the terrain where the CPT had to be performed. And obviously he landed in a ditch because the terrain was not sturdy enough. There was no adequate working platform for him to travel those last couple of yards to the actual location of the CPT site. Unfortunately, nobody got injured. Nobody died, and with the crane we were able to get the truck out of the ditch and repair it in the end. But those obviously are incidents as well that are related to travel to and from the job site that we need to keep in mind. So that's number one. The second aspect, and again, nothing related to CPT per se, is know what is below. If we are performing CPTs, you generally go into areas where there's already other construction, other underground utilities that are there that you obviously should miss. You should not try to puncture a pipeline or a cable, and that is why it's very important that you know what is below. I've taken some pictures here from posters that are being utilized in the United States where you can dial 811. Around the world, it may not be the case, but the message remains the same. Underground pipelines are everywhere. Underground cables are everywhere. So know what is below before you start your CPT, because obviously those things can go wrong or can cause problems, and you want to avoid those. So travel to and from the job site, know what is below, two most important things to make sure that your CPT goes well. But now let's look at CPT itself. And the first thing that I want to look at is verticality. Let's start with some text out of the standard. Like I told you before, when you see a blue box in this presentation, it basically means that the text comes straight out of the ASTM standard. Push rods can be damaged or broken under extreme loadings. Well, makes sense. If you load them too much, they get broken. Excessive rod deflection is the most common cause for rod breakage. What is meant by that? Let's go back to a figure that you've seen, I don't know how many times, for those of you that have attended these webinars in the past. I pretty much show it every webinar because it gives a very good overview of what CPT is all about. You see the cone truck pushing the cone into the ground with the rods, and we've talked about the cone and the sensors that are in the cone, be it to measure the tip resistance, the pore water pressure, or the sleeve friction. But what I focus on today is the inclinometer that you see there just above the friction sleeve. Because with that inclinometer, what you can do, you can monitor while you're doing your CPT the inclination continually. And it's very important for the operator that he always knows what is the inclination of the cone. Does it go down vertically, yay or nay? And why is that? Well, ideally speaking, you want to see something like this. You start at a surface and you go perfectly vertically down. That is what you try to obtain. That's what you see the picture on the right-hand side as well. I always show that those rods go perfectly vertically down into the soil. But the reality is, that's not always the case. What you see here is a rig that has been positioned. You see that it's off the ground. The hydraulic legs are there. It's anchored in the ground with the ground anchors, and we're ready to begin pushing. Except that the rig is not level. And if it's not level, you will start under an angle pushing your cone into the ground, and that means that you will never go vertically down. So the first thing that you need to make sure is that when you are getting ready to push your cone into the ground, that the rig is perfectly level. But it's only part of the story. Because when you go into the ground, you undoubtedly pass alongside obstructions, some boulders, some cobbles, some coarse gravel, whatever it is. Maybe you hit some inclined dense layers, because the transition between one layer and the next isn't always a perfectly horizontal line. It's angled, it's inclined. And that may deflect the cone and induce drift. But you get something like this. Levels your rig perfectly. You start pushing your cone, it went vertically down, no problems, and then suddenly something happens and the cone direction starts to deflect, and you are no longer going vertically down. And that could pose a problem. Why? The significant bending of the push rods can influence the penetration resistance data. Illustrated by this figure here. Let's look at the cones that are pushed in the ground. At the surface, you think that you've pushed about 36 meters down into the soil. Why 36 meters? Well, you've used 36 rods, and therefore your depth should be about 36 meters. And you see on your screen the solid black line, which is the tip resistance. And you come to the conclusion that, well, somewhere around a depth of 30 meters, that's where this stiffer layer is starting to begin. Now, if you were to pass this information on to your client, and he is using that to design something, during the construction phase, they'll find out that that layer did not start at 30 meters, but at 25 meters. Because the real vertical depth where the cone was not something like 36 meters. It was closer to about 29 meters because of this extensive deflection. Now, in reality, I don't think this is going to happen, that you're pushing on a 45-degree angle, but you get the picture. Yeah, if you have significant bending, you can have resistance data for which the depth scale is no longer accurate. But that's not all. Because the other thing that may happen is that as you're doing this whole thing, it can cause a fracture. Go back to this figure. Pushing it in the ground at the top, a certain force. Let's assume that there's no friction along the rods. So you have all that force goes to the tip. You start seeing a bent structure. And invariably, if you're pushing that on both ends, you can imagine it's probably going to snap. And that's the fracture that we're talking about, and that's what we want to avoid. Now, how can you visualize it better? Think of a Ford F-150. Let's crush the darn thing and put those Ford F-150s on top of each other. Unfortunately, I could not find a picture of a crushed F-150, so you have to do it with this picture. But 10 F-150s, pickup trucks, crushed, stacked on top of each other. Also think of a 4-story building. And what CPT really is all about is that you put a little slender pole, roughly the height of that 4-story building, and you balance those 10 F-150s on top of it. That is what CPT with a 20-ton pusher is. And here it looks already pretty unbalanced. It's pretty scary that you have those cars balancing on top of that red line. In reality, the red line is way too thick for the scale that's in. So it's a very slender pole that you're pushing into the ground. And if that starts to bend, yeah, it makes perfect sense. It's very understandable that the thing starts to break or could break. So what does the code say? Well, limitations on inclination in the system should be imposed. Makes sense. And it gives some recommendations that you should have no more than 1 degree change in inclination over 1 meter of penetration. And the total drift should be limited to no more than 15 degrees. If you do that, you have a very good chance that everything will be fine. At least you have no unreliable resistance data based on this huge deflection. But there's one thing that's very important to remember here. Even if you have sounding is particularly vertical, the rods may still break because of buckling. Because what the whole theory assumes is that you have continuous lateral support, either from the soil or from casing that you put around the tubes. So if you are in a place or in a condition where there is no lateral support, because you go through water or very soft soil, and then please make sure that you don't rely just on the verticality. Make sure that you provide that lateral support as well by placing casing. An easy rule of thumb is, if you just let your cone go down on its own way, that you don't have to push. Because let's face it, if you put it go through water, the cone will go down all by itself. If you're very soft soil, the cone and the rods on top of it will go down all by themselves. As long as it goes down on its own weight, you need to push casing. So you let it go down on its own weight. And when you need to begin pushing, that is the time that you stop your CPT, you place your casing so that you have the lateral support. So, conclusion of this first part, control the inclination to avoid a fracture and also inaccurate data. But remember, it does not need to break for there to be a problem. And that brings me then to the next part, and that's the cone performance. First, look a little bit at the load cells. Take, for instance, the load cell that is there for the tip resistance. If you start hitting a little obstruction in the soil, you may start to increase your load quite a bit. Let's look at it a little bit more in detail. Say that you're pushing with a 20-ton pusher, 100 kilonewtons. You have a 10 centimeter square cone, and you have a load cell that is rated for 100 MPa. What's important here is not necessarily the units, because I could have put it in tons and in kips as well, but what was most important is just the principle. Pushing with that force on that diameter cone basically means that the load cell could see double the value it's rated for. And obviously, it will cause a problem. That's why the code says that refusal, flexion, damage to the cone may occur in coarse-grained soil deposits with a maximum particle size that approach or exceed the diameter of the cone. That's why you see that little part there underneath the cone tip. But it could also be much bigger. And that's what something that I've mentioned in the past as well. People try to keep pushing through rock or through construction debris, pieces of concrete. It will not work. You will very easily overextend your load cell. And when you do that, your cone is going to be broken or no longer functional, and you have a problem. So that's something that you need to be aware of and avoid. That's one part of the cone. The second part of the cone is the pressure sensor for the pore water pressure. What's really important to remember is that when you push the cone into the ground, and we've covered this in the past as well, you don't measure the hydrostatic pressure, but a dynamic pore water pressure. That's illustrated here. We're pushing the cone onto about a level of 7 meters, and that's where the water table is. And then the hydrostatic pressure is shown by the dotted blue line. In reality, though, that's not what you measure. You measure the dynamic pore water pressure, and what you see here is reflected in the solid black line, and that obviously in lots of places is much greater than the pore water pressure that you have for the hydrostatic pressure. Now, to give you an idea here, when you talk about 14 meters, you should have somewhere a pressure of about 0.1 megapascal. In reality, you have one that's 0.8, so about 8 times higher. And it's very important to remember, especially as you go deeper, because the dynamic pore water pressure can be much higher than the hydrostatic pressure. And it's illustrated in this chart, in this graph, where you see that at the U2 position, where we generally measure the whole thing, if you have your hydrostatic pressure here, it could be 10, 15, or even more factor or times greater than the hydrostatic pressure. So it's important that you remember that your pore pressure that you read is much higher than the hydrostatic pressure, and that you should size your pressure sensor for that. Otherwise, your pressure sensor will fail, and we have a problem. So that's the second one on the cone. Third part, as we keep moving up to the cone, the friction sleeve. And the friction sleeve, for it to function properly, needs to be able to move up and down freely. Only then it can record the sleeve friction accurately. It means that the O-rings on either side of the friction sleeve, they must be flexible enough that that friction sleeve can move up and down. And if there's dirt in those gaps where those O-rings are, and that is dried out, is caked up, then that friction sleeve can no longer move. And therefore, you don't measure your friction accurately. The code talks about it as follows. It says soil ingress between different elements of a cone, the gaps that I just mentioned, can result in unreliable data. Specifically, soil ingress will detrimentally affect sleeve resistance data, and seals should be inspected and maintained regularly and replaced when necessary. Makes perfect sense, but something you need to think about, and that's why cleaning the cone is something that is very important. Finally, when it comes to the cone performance, I want to mention one other thing. Electronics inside the cone, because what you see there is a demo version we took also to a conference where it was last week at the IFC conference in Dallas. That's just a model of the cone cut open, and you see the load cells in there. That electronics cannot get wet. If it does get wet, you have no longer reliable data. And that basically means when seals that you have there should not just be inspected for the reasons that I just mentioned before, that your friction sleeve can move up and down freely. Now they should also be inspected regularly for overall condition, cleanliness, and water tightness. Because if they're not watertight, if there's a small hole in there, if they're not thick enough anymore, because they're worn to the extent that there is no water tightness, then you're going to have a problem, because if water gets inside your cone, you're sunk. Basically, your cone will no longer function. So, with that, when it comes to the cone performance, it's important that you give the cone proper care, that you inspect it, that you look at it on a regular basis, and that you also think that the cone design is appropriate. Now, when the rods that we're using, by and large, when you buy CPT rods, those rods you use all the time. But a cone, if you don't size the pressure sensors or the load cells appropriately, you can easily damage the cone. It's important to remember, a cone is not just a piece of steel. It is a very sensitive instrument that can give you very good data, very accurate data, as long as you take care of the cone. And that's why I started out with give the cone proper care. Brings me then to the end of my presentation for today. And again, what I want to emphasize there is that you need to make sure that you recognize that you're pushing a very delicate instrument. That's especially the cone. We talked about it. But you're also pushing it with an awful lot of force, using a very slender pole. Keep in mind that as you are using the cone into the ground, even if you're not using with a 20-ton pusher, you're only using it with a 10-ton pusher. Okay, fine. It's not 10 F-150s on top of the whole thing. It's 5. But still, 5 F-150 pickup trucks are sitting on top of that little slender pole. And that's why you need to be careful, because that force is quite a bit. And finally, be careful on the road. Because as I started out, it is not just what you do on the job site, it's traveling to and from the job site that also has its risks. And it is quite often a much greater risk than what will happen on the job site, provided you know what is below. If you are in an area where it's obvious that there are utilities, that there are potential pipelines there, don't just start pushing. It was about 1.5 years ago or so that somebody who I was working with got very lucky. There were side by side a water main and a high voltage electricity cable. He hit the water main. It was big damage. A lot of water got spilled, but it was in the end much safer. If he had moved a little bit over, he had hit the power cable, which would have been much more serious. It's important that you know what is below. And with that, I can go to some questions that we have for this event. One question that came in was basically, is this all? No, it is not, but I only have about 25 minutes. There are all kinds of horror stories. When you're pushing your cone, you know that generally speaking, you may not have sufficient space inside your cabin. Therefore, you put up a little parapet and then make sure that you have a little bit more working space. And sometimes your rod sticks out of the roof of the vehicle. before you leave the job site, make sure that everything is put back down again. Also, when you have a cone in the ground, don't try to move your truck. You may say, well, that's pretty obvious. It's about 8 or 9 years ago or so by now. I was on a job site. Somebody was doing some CPT work and was asked to move the truck. And he had to do it right now because there was a large truck with cargo coming through there, and this CPT truck was in the way. The person was somewhat flustered, so he stopped his CPT with the rod still in the ground, moved his truck, and you can only begin to imagine what the consequences are. No, there are other things, and that is where experience comes in. Be careful that you complete your job, but the ones that I've covered here are the most important things. And really, if you ask me personally, the thing that you need to be most aware of is traveling to and from the job site and know what is below. It has nothing to do with CPT per se, but those are the most important things. The other questions are very specific. I will come back to those to the people through an email, because they more reflect certain situations that they have with certain providers. So we'll leave that for email exchange with those people. What I would like to do now is thank you for being here. Thank you very much. Thank you for being here, and look forward to seeing you in the future. And in the meantime, keep performing those CPTs. Thank you very much.